Awesome.
Great.
Okay. So mainstream theories of visual working memory construe it as a durable short-term memory store, meaning unlike iconic memory, it is relatively resistant to masking effects, as well as potential interference from shifts of attention between items in the external environment. So in this talk, I'll talk about some data by Mycoskie and colleagues that appears to challenge this mainstream view. And I'll also talk about an alternative explanation for their results that rests on the assumption that people might use different strategies in the standard single probe change detection task. So the specific study I'll focus on first was run by Mycoskie and colleagues in 2010. And in several experiments, they found that performance as measured by D prime was better in a single probe change detection task than in a two alternative force choice task or a 2AFC task. And based on these results, the authors concluded that attending to two probe items in 2AFC instead of a single probe item stimulus as in the single probe change detection task may lead to interference effects. So together, these results were interpreted as indicating that visual working memory was more fragile or less durable than previously thought. And these results are puzzling because they appear to undermine mainstream models of visual working memory. Also, there's an intuition that maybe having more information when you're probed for memory, as you do in the 2AFC task, should help performance because you have more information to constrain your memory judgments. And so we considered an alternative explanation for these results, which is that performance is not worse in the 2AFC task, but people use a decision strategy in some versions of the change detection task that's not being taken into account. And before describing this decision strategy, I will need to quickly review some assumptions of signal detection theory, which determined how Mycoskie and colleagues calculated D prime in these two tasks. So in a single probe change detection task, people make a judgment on each trial about whether a change or no change occurs. And so let's assume that people define the signal in terms of detecting a change. So in each trial, they're trying to judge whether the probe item changed from a memory item or not. And so the red distribution here, which is centered at 0, represents evidence for a change on no change trials, and the black distribution centered at 1.5 represents evidence for change in change trials. So here D prime reflects the standardized distance between the noise and signal distributions. Now in a 2AFC task, the decision axis is different. So now people are always shown both the old target item and a lure. So strictly speaking, there are no noise trials like there are in the change detection task. So instead, people need to judge whether the item on the left or the right is a target item. So imagine we define the signal in terms of detecting the target when it is on the left. And so to do this, we must consider trials in which the target is presented on the left and trials in which it's presented on the right. So consequently here, D prime reflects the standardized distance between two signal distributions, one of which is centered at 1.5 and one which is centered at negative 1.5. So I'm going to summarize a few very basic assumptions that follow, which will guide the logic of the experiments that I present to you. So first, if we assume that this is how people do the change detection in 2AFC task, there's a simple transformation of D prime on the 2AFC task that can give you D prime on the change detection task. So as you can see, if you divide D prime on 2AFC by the square root of 2, you should get, or this equality should hold. And under these assumptions, it should be obvious that if we don't divide D prime on the 2AFC task by square root of 2, it will be larger than it is in the change detection task. However, if people use a strategy that turns the change detection task into a 2AFC task in a way that I will describe shortly, D primes across the two tasks should be equal to one another without the square root of 2 correction. So now I'll describe the decision strategy we think people might use in the single probe change detection task. So here we assume that lure items in the change detection task are always an item that wasn't present in the memory array. So in that case, it is common for researchers to use lure colors that are a fixed number of degrees away from the target in color space, or that are from a very different color category. And so what we thought is that maybe people use this information about the color of lures in the change detection task to inform their memory judgments. Specifically under these conditions, people could functionally turn the change detection task into a 2AFC task by considering what the item may or may not be. So for instance, if they're shown an old item that is purple and know that the other items are very different from the target item, they may recall a green item to compare to the probe item. So in this scenario, you have two sources of information to constrain your memory judgments, and you can use a process of elimination type of strategy and decide that since it's definitely not the green item, it must be the purple item. So this type of recall strategy is actually consistent with a well-known strategy in the long-term memory literature called recall to reject, which refers to how people might recall items that are similar to a lure item and then use evidence from both to make a memory judgment. And it's also consistent with some evidence that people may employ memory search strategies in saying different perceptual judgments. So to test this prediction, in our first experiments, we had two different groups of participants separately complete two versions of the single probe change detection task, which I'll describe in a second. And in both variants of the change detection task, they could predict the lure color because it was 180 degrees away from the target. And so we expected that under these conditions, people might use the strategy and turn the change detection task into a 2FC task. And then we had a third group of people that just completed the 2FC task. So here's just a summary of these assumptions that I showed you before. So what we wanted to see is whether D primes in the change detection task and 2FC task were equal to one another without the square root of 2 correction that we would use under standard assumptions. And so the type of memory probes in each experiment are shown below. So in the 2FC task, people are shown two stimuli at tests and are asked to report whether the one on the left or the right is a target. There were also two versions of the change detection task, one where the probe stimulus was presented in the center and one where it was shown in the original location. And so we used both of these versions of the change detection task because we wanted to test the prediction of Mycoskie et al. That shifts of attention in the 2FC task may create interference costs that hurt performance in these visual working memory tasks. So if this is the case, performance should be worse when the probe stimulus is presented in the center than when it is presented in its original location. And in all of these experiments, we estimated D prime by fitting models to ROC curves. So we constructed ROC curves, ROC curves are just people's performance plot, hits plotted as a function of false alarm rates for different levels of people's response bias. And we measured response bias using confidence ratings. And so we just fit models to these empirical ROC curves to estimate D prime. And so the results were consistent with our prediction. We found that the data in the change detection task conformed with the prediction that people were turning the change detection task into a 2FC task. That is, D prime in change detection was not statistically different from D prime in 2AFC in any of these tasks. So the results from experiment 1 provide tentative support for view that people might be turning the change detection task into a 2FC task. They remain very provisional since they rest on accepting the null. So in experiment 2, we wanted to test our predictions in a different way by examining what happens if we break down the predictability of lure colors. And so because this should prevent people from turning the change detection task into a 2FC task. So to do this, we had two separate groups complete the change detection task. The mixed lure group was presented with lures that were either similar, so close to the target in color space, or dissimilar from the target, so 180 degrees away from the target color space. And then there was a different group who were always shown lures on change trials that were 180 degrees away from the target. And so we predicted that people should use this recall strategy in the different lure group, but not the mixed lure group. And shown here are the ROC curves for both groups. And so the first prediction we made is that people in the different lure group are treating the change detection task like it's a 2FC task. So if we don't apply the square root of 2 correction, their D prime, or here mu estimates, should be larger in the different lure than the mixed lure group. And that is what we found for both set sizes. So as you can see, when we condition our analysis on just trials where the lure is 180 degrees away from the target, mu estimates in the group of people who are always shown lures that can be predicted are higher than they're in the group where lure colors cannot be predicted. So finally, since we fit signal detection models to our ROC curves, we could test between an equal and unequal variance signal detection model. And so what we would predict in a standard change detection task is that the unequal variance model might outperform the equal variance model. And this is because the unequal variance model would capture things like effects of item variability and performance. In contrast, if people are turning the change detection task into a 2AFC task, we should find that the equal variance model performs the best because the equal variance model will always perform the best in a 2AFC task. And one way of thinking about that, why that is that the 2AFC task obfuscates effects of item variability. So based on these assumptions, we predict that the equal variance model would perform the best in the different Lohr group, and the unequal variance model will perform the best in the mixed Lohr group. And that is what we found. So shown here is delta AAC, so smaller values are better. And you can also see this from the ROC curves themselves. So specifically, ROC curves are curvilinear but symmetric in the different Lohr group, which is consistent with an equal variance model, and then asymmetric and curvilinear in the mixed Lohr group, which is consistent with an unequal variance signal detection model. These are aggregate data. So in conclusion, we point out that decision strategies determine how we can interpret metrics of performance in visual working memory tasks. And the experiments I presented to you today suggest that people might not be worse in a 2AFC task than a change detection task. Instead, they may employ different strategies in change detection tasks, which can inflate estimates of visual working memory sensitivity if they're not taken into account. Thanks.
Great talk. Good timing. I think we have a lot of time for questions. So let's see who is going to start first. Anybody from the audience wants to ask questions to Maria about the strategies that people are applying, change detection and 2AFC tasks? So yes, Klaus Oberauer. I can see how your strategy works if each target is related to exactly one change probe, but that's usually not the case. So how can one know the possible target from the probe?
I think I didn't quite, so sorry, what do you mean by one target is related to one probe?
Sorry, I mean, this is based on how I understood that strategy that you mentioned to work. So what I understood is that if you see the probe and you can use the information in the probe to reconstruct what the target would have been if this is a change trial, then you can mentally put them side by side and turn it into a 2AFC, right? Mm. And I can see how that works in your first experiment, where any change probe is always exactly 180 degrees away from the target. So I can basically rotate it back 180 degrees to its possible original, right? And I know exactly what the target would have been. But in a typical change detection task, the change is usually big, but that doesn't mean that there's only exactly one change for each possible target. So when I see a probe red, then I know the target could have been green or blue or yellow, but I don't know which, right? So how can I turn that into a 2AFC?
Yeah, that's an excellent question, and that's something we're kind of trying to also think through. We've considered slightly different variants of these strategies that maybe people actually take something like the difference between each color and an ensemble of all color channels. That might not quite lead to the same predictions about the fit of the equal variance and unequal variance model. But yeah, I don't have an answer that I'm totally, that I think is a totally solid one. But I guess one possibility is just that people recall just a single color from a different color category because they know that the colors will always come from a different color category, and they just sample one of those items, or maybe iteratively sample one item and then just make their judgment based on the last comparison. But yeah, I don't, I think that's an excellent question and something we need to think about.
Thank you.